Hello everyone, welcome to Fresh Concrete. This is the second of this year's Fresh Concrete events, which is produced in collaboration between the Concrete Centre and the Building Centre. My name is Elaine Toogood. I'm Director of Architecture and Sustainable Design at the Concrete Centre, and I will be hosting today's event and introducing you in just a minute to our speaker. I can't wait. So this online series has been created to share just some of the wide-ranging innovative practices and types of concrete that are emerging to address climate change. And these are technologies that bring a fresh approach and a fresh thinking to the way that we make and we use concrete. So the recordings from last year's series are now all available online to look through, and you can see them on these links on the screen. If you haven't already, I urge you to take a look. There's some really interesting and thought-provoking innovation in the manufacture and use of concrete in construction, including carbon capturing concrete, graphene enhanced concrete, a structural design that's been developed to be de- and reassembled, self-healing concrete designed in a form to enhance biodiversity, and also concrete that can help passively charge vehicles that drives over it, and also 3D printed concrete. Now, 3D printed concrete is also the subject of today's talk again, but this time really pushing the boundaries of what it can do for us in the creation of structural beams. And I am delighted to be welcoming Andy Coward, who is founder of Zero Projects and MinimassTM, to explain his innovative structural solutions, its benefits, and the opportunities that it can offer. Now, while Andy just gets himself ready and starts to share his screen, I will remind you that there will be time for questions at the end of this session. And so as we're going along, please do put your questions for Andy in the Q&A box at the bottom of the screen. And I shall endeavour to ask as many of those as I can at the end. Now, if we don't manage to get through all those questions, we will share that list with Andy afterwards to respond to you directly. So if you would like to do that, then please do. If you don't want a follow-up question, then please just ask your questions anonymously or let us know when you write your question. So I shall now stop sharing and hand over to Andy to better do that and welcome him. Put his fantastic. Andy, welcome.
Thank you very much.
Excellent. So you're there. So brilliant. So I shall now hand over to you. I'm going to stop sharing my screen. And please, over to you for the presentation. Thanks very much.
Okay, thank you. Thank you very much, Elaine. Hopefully everyone can see me and hear my see the screen there and hear me as well. So I'm going to talk to you today about MinimassTM. This is an approach, hopefully, that many people will recognize, trying to do more with less. I'm a structural engineer by background with over 17 years in the industry. I was at the University of Cambridge in the early 2000s before going, unlike most of my peers, unfortunately, going into the engineering industry and joining AECOM, or Oscar Faber as it was then, which shows how old I am. I moved from there to Foster & Partners, where I was part of the in-house engineering team with them working on projects all around the world, which was a very lucky position to be in. And then a few years after being at Foster's, I was moved to Copenhagen, where I joined Bjarke Ingels Group, also an international architecture firm, rising to Director of Engineering at BIG, until the point at which I started my own company in late 2021. So that's what I'd like to talk to you about today. So to set the scene, I'm sure we talk a lot, certainly in the concrete industry, but throughout construction, about two of the big challenges that we face. One is cost, and everyone talks about cost almost all the time. The other is now carbon, which when I first started work wasn't something we talked about at all, and is again now something we talk about a lot. So I'd like to say that as a designer, I would now focus on both of these aspects just as much. The Concrete Centre is at the forefront of many of these things, in particular to do with concrete. So specifying sustainable concrete is something which we should all have as a document on our desks. But if you don't, I'm sure you'll be able to get hold of a copy. From my point of view, the way that I have chosen to address cost and carbon is using my background as a designer. So I'm not a materials scientist, which means, unfortunately, I can't invent low carbon concrete or zero carbon concrete, but I wish I could. I'm not a sort of robots guy. I'm not a software programmer or any of those things. I'm a designer, and I'm confident with the codes and all of that. So my approach is to use less material, use less labor. Therefore, you have less cost and less carbon. Simple, really. So just in a very brief way, this image shows an example of one of the members of the family of Minimass beams, specifically beams, which could, without doing anything to the materials, give you up to a 70% reduction in embodied carbon compared to a similarly performing concrete beam, and up to a 50% material cost reduction. So here is a slide I like to show on every presentation. I sort of shoehorn it in everywhere I can, because these are some of the most fantastic structures from my point of view, built during, I think all of them, during the, or certainly most of them during the 20th century. Yes, that's right, most of them during the 20th century. And the thing which joins these structures together is their fantastic use of in-plane forces, tension and compression, rather than relying on bending. Bending is a habit that I would say the engineering industry got into in the late 20th century when materials became less expensive and labor became more expensive. Well, we're at a point where I believe the situation has switched again. Because of carbon, materials are becoming more valuable. So we need to start thinking about how we can use materials in an efficient way and get back to the kinds of fantastic geometries that we're seeing here. So what is Minimass? Well, first of all, I'll tell you that it's inspired by work that's gone before. As soon as anyone invents anything, they realize pretty quickly, and certainly this was the case for me, that actually you haven't invented something, someone got there before you. And that is, in truth, a very reassuring thing, because it means you're not going crazy and you haven't sort of fallen off the map. So here are just a few examples of bridges that at a very large scale do exactly what I'm trying to achieve with Minimass. They are separating tension and compression elements. So they are achieving a bending structure by using tension and compression. And that's the principle behind Minimass. This on the left here, Eurocode 2, figure 3.5, should be seared into the minds of all concrete designers. So hopefully you recognize it. This is the idea of the rectangular stress block distribution and where your compression and tension goes. So even if you don't realize it, when you design a bending structure, you are in effect designing for tension and compression, certainly at the ultimate limit state. So if Eurocode 2 suggests that the concrete effectively below the neutral axis is ignored, then the question I ask myself is, can we remove that concrete that we're not using in our strength calculation? You could say, well, I'm just in a roundabout way describing another type of truss. So is this another type of truss? On the screen, this is not a concrete truss, this is a steel truss, fourth rail bridge. But yes, in some senses, Minimass is another type of truss because I'm trying to shape the geometry to match the applied loads. But it's not a typical truss, certainly because most trusses that what one would design would be out of steel or perhaps timber. They wouldn't typically use concrete because the history of concrete trusses is sort of not very widely spread, typically because connections are difficult, reinforcement is difficult. The other thing that, so I'm trying to use concrete specifically for compression because that's placing the right material in the right place, but also because I'm also trying to avoid tension in the web members. So your standard rectangular truss would end up with alternating tension and compression in the webs. And I'm looking for something that has compression only. And I do that using graphic statics, which again, I'm sure is familiar to many of the people on the call today. Graphic statics is a very powerful concept tool. I wouldn't describe it as anything that would go into detailed design necessarily, but for concept and for geometry generation, it's fantastically powerful. And I have sort of fallen in love with it to a certain extent. And this on the page is the constant force truss, which does exactly what it says. It enables you to generate a geometry that gives you a constant force in your bottom chord. In this case, tension, constant tension force in the bottom chord, described by the blue line here, which responds to a uniform load. The nice thing about the constant force truss is that the red lines, everything else, the web members and the top chord, are in compression. And so that achieves part of what I was trying to achieve with Minimass, to have tension in the bottom and compression everywhere else. The other nice thing about graphic statics is that it allows you to explore different geometries under different loads. So if you had, for example, not just a uniform load, but a point load like a transfer beam, you could vary your geometry and still maintain a constant force in the bottom chord and still maintain compression in the rest of your geometry. So here we go. When you apply that type of thinking to a Minimass beam, it is possible to generate these two families on the left and in the middle, which are concrete trusses, let's call them Minimass beams. They have a concrete top chord, a steel bottom chord, typically made using post-tensioning strands, and concrete webs to separate the steel from the concrete in the top chord. The geometry of these can vary depending on, of course, the length, but also depending on the applied loads. I've indicated them as two families, MM01 and MM02, because there are two different possible approaches to how you might consider the concrete itself. So on the far left is something that I've indicated as unreinforced. So that would be applicable to concrete where we're using Chapter 12 from Zero Code 2, which would be plain concrete. So there might be a little bit of reinforcement running along the length of the beam to allow you to lift it up, and for moving it around on site and robustness and those sorts of things. But basically, at the ultimate limit state, it's taking its compression capacity only. And it could be a piece of masonry, it could be a piece of stone, it could be glass, it could be anything that can take compression. At the ends where the steel joins the concrete, there would be bursting reinforcement for the high transfer of forces, and that would be detailed in the normal way. So there'd certainly be reinforcement in those locations. In the middle, there is another version where this can best be described as a reinforced concrete version of the Minimass beam. And that's where we would be following all of the code requirements in Eurocode 2 for reinforced concrete. And so would certainly have reinforcement along the top chord. The two would be, broadly speaking, applicable in roof situations for the unreinforced version and in floor situations for the reinforced version, typically because the stiffness of the reinforced version is significantly greater than the stiffness of the unreinforced version. On the right there, you have a traditional concrete beam. Each of these three sets of images has the same performance requirements, so responds to the same loads over the same spans. So you can start to see a significant saving in concrete material and steel material in this case. So I've been pretty careful so far to avoid using the phrase 3D printing, because everything I've described up till now can be achieved purely through geometry. It would be possible to make, if you had a precast factory that was set up in such a way, it would be possible to make a Minimass beam using precast techniques, or indeed in situ if you had the time and the labor. So that's worth pointing out. However, I have gone down the route of 3D printing because I think it offers fantastic opportunities to create expressive structures using complicated geometries without the cost of the labor, and certainly with a very fast turnaround time, mass customization, if you like. So the evolution of the industry from in situ to precast, I would propose that the next step is a 3D printed future. So here is a version of 3D printing. I'm sure many of you have seen images such as this online. It's reassuringly calm, if you like, just like squeezing toothpaste out of a tube. This is a version where you're able to place reinforcement along or across the length of the print, but not through it. So this would be something which you could describe as unreinforced concrete, because in this orientation you can't put shear links in it, so that wouldn't necessarily pass those values. But this would be a version where you could place reinforcement. So this is a different geometry. It doesn't look like a beam, and certainly if anyone wanted to know more about why this shape is how it is, I can talk about it at great length afterwards. But let's say this is the second version where we're printing the perimeter of a geometry, and then we're able to place reinforcement inside the perimeter or within the perimeter and fill it up with concrete. So the best way to describe the version for a reinforced concrete mini-mass beam is that we're printing a permanent formwork that we then fill with rebar and with concrete, which could be the same mix as the print itself, or indeed it could be a different concrete mix. For example, if you have something with a particular low carbon concrete mix. It doesn't have necessarily a very good finish when you start off by printing it. It's worth noting that this is printed concrete, not mortar, because we're using a 10mm aggregate. So it is actually concrete with additives rather than a sort of complex mortar or grout. You can see here with the flaps on the printer, then we get this nice smooth finish. This is using machinery from Cobod, one of the big 3D printing manufacturers, and working with a company called HTL Technologies. There we go. And when we add all of these things up, then the sort of value proposition here is that for like performance, in this case a 9-meter beam at a 9-meter spacing supporting office-like loading, a mini-mass versus a traditional reinforced or precast concrete beam, we can generate a reduction in concrete of around 5,000 kilograms, 5 tons, reduction in steel in the rebar of around sort of 400 or 500 kilograms, and an overall reduction in embodied carbon of up to 70%. This is a bit more detail about how these things work. So in the case where we're taking the top chord as a reinforced concrete member, then the graphic statics implies that you have point loads at the nodes. That is not a very realistic case. In most cases, you would have a uniform load. So in actual fact, you do have some bending moment in the top chord. But the bending moment on the left-hand diagram here is the critical thing, because the dashed black line is your typical WL squared over 8 beam span bending moment. And the solid red line there is the resulting top chord bending moment. So we're designing our top chord for a compression force due to the push-pull and a significantly lower bending moment. So the reinforcement, therefore, on the top chord is less. Interesting to point out that the dashed red line on the left-hand side is the bending moment associated with the live load applied to half of the span. So that's the typical case when you have half span loading, a sort of pattern load, and that can be the thing which governs the design. On the right is the shear. Because of the inclination of the cable, it's actually the cable which does the majority of the shear work. So you have a massive reduction in the peak shear that you have to design the concrete for. Again, so that means we're able to be very efficient with the shear. I won't go through this in great detail, but there has been independent cost comparisons done. So for that same 9-meter mini-mass beam or supporting the same loads, the cost on site is roughly £3,500 for a mini-mass beam. This was as of January 2023, around 5,000 for a steel beam, 5,500 to 6,000 for a traditional precast concrete beam, and something like 12,000 for a glulam beam. So glulam at the moment, the information I have is that it's off the map in terms of cost, but Minimass is cheaper than the alternative. So we get on to some details here. Worth saying that Minimass is not really appropriate for very short beams. If depth is the most critical thing, then stick with steel. If you're building a house and you need a joist, or you've taken out a wall or something, then steel's the answer. If you get to the 6 to 12 meter lengths, then Minimass is very competitive, and longer than about 12 meters, where self-weight really becomes important, then Minimass is an excellent option. Fire is very important with the exposed cables below. It's possible to have sheathing for these PT strands, which has an embedded intumescent layer. That's quite common in the US, and is certainly used in seismic retrofit over there. It's more common in Europe to use grouted PT, so certainly it's possible to place the cables within a duct and then a second duct around it that you can then grout, and that will give you the cover that you require. It would be possible to apply a coating on site, but that's a pretty awful job. In terms of details, the version I'm going for at the moment is a kind of composite, where the slab, if it's concrete, is part of the top chord. You can then pass your surfaces through the webs. Similarly, you can work with CLT. I think CLT and Minimass is an excellent hybrid option, because that would really allow you to drive carbon out of the structure, but release yourself from the 6 meter grid that a typical CLT building has. And then there would be details at the end, connections for tie forces, robustness, all of the usual sorts of precast detail. A couple of case studies. I'm conscious of the time, so I'll whip through these as fast as I can. It looks like the first structure that will be built is going to be a road bridge in Ukraine. So up to now, the business has been on an R&D footing, and we're now moving towards pilot projects. So this is likely to be the first bridge. It's 8 meters long in terms of bridge span, so it's not a big one, but it's designed for full road loading. It's going to be as part of a reconstruction project in a war zone, so we're designing for very heavy loads. But it's allowing us to span twice as far within the same depth as the previous bridge that was there. This is the kind of detail that we're looking at. So it's definitely a hybrid construction, where we have our 3D printed beam as part of the depth, and then a sort of lattice slab, biscuit slab sitting on top that we cast up with concrete. A second case study is for a building here, one of those situations where you have residential on top of retail, and you have the challenge of changing your grid so that you no longer have the dense structure that you typically have with residential running through the retail. This was designed with a concrete flat slab as a transfer slab. Now, if we want to save carbon, there are many solutions for reducing carbon compared to a thick concrete flat slab. So I'm not suggesting that Minimass is the only one, but Minimass is a good one because it does allow you to switch to something with a lower carbon footprint in the slab structure, like CLT or like hollow core. But it also allows you to tune the deflections and the stresses in the cables to pick up the permanent loads from the transfers. So that's very positive, and therefore, if you wanted to, you could span further and remove columns. The last thing just to touch on is that there has been quite a lot of physical testing that's gone on. I've done load testing at laboratories in the Danish Technical University in Copenhagen, and I've also done a fire test, significantly fire test over in Belfast with Effectis, the company. And so we did because the furnace was 2 meters long, we did a 2 meter long beam with a 20 kilonewton point load. So not very heavily loaded, but we did a small beam that was exposed without any fire protection, so no coverings to the cables, for 132 minutes at 1100 degrees C. and it performed very well. It showed very few signs of damage. Partly, of course, that's because the load itself wasn't very high, and partly because it was able to transfer the load from the force in the steel as the steel reduced its strength to the concrete itself. This is what it looked like. Well, this is what half of the beam looked like after the test. So you can see something's happened to it. It looks a bit rough. The steel is a bit rusty. It's definitely affected by the 1100 degrees C, but it's remarkably good condition. No spalling and no sort of major deflection cracks or anything like that. This was on display at my stand at Future Build, if anyone was there earlier this year. Right, I'm going to say that's the lot, and open it up to any questions.
Thank you very much, Andy. That was excellent. And if you could stop sharing your screen, and then I'll ask you some of the questions, if that's all right. So great, excellent. So we've got a few questions here, which I will run through some of them. There's quite a few. There's a lot of interest, I'm happy to say. So first one is, does the MiniMass beam require more steel than a conventional beam? Now, I don't know if that is referring to a steel beam or a concrete beam. You might be able, but also have you factored that into the calculation with your net carbon gain or loss? So
yes, certainly looked at comparisons, and I have tried to be as strict as I possibly can in terms of comparisons. So a reinforced concrete versus MiniMass beam, there's definitely a reduction in the quantity of steel in terms of mass. There's less rebar. I know there is a switch from rebar to PT steel, which comes at a higher cost and a higher carbon, but because it's such a significant reduction in overall mass, there is still a reduction in carbon and cost associated. Compared to a steel beam, then it's more difficult to make a direct comparison in terms of mass of steel versus mass of rebar, but there is still certainly a reduction in carbon. So it's not as much as 70%. What I found is it's more like 40 to 50% embodied carbon reduction compared to steel structures.
Okay, excellent, thank you. How does MiniMass react with vibration? Is that something that you've
yes,
looked at?
Very good question. Of course, because we're taking some of the stiffness away, that a large rectangular section is stiffer than a T section, then in principle it is worse performing under vibration. But really what that means is that vibration becomes a more important load case to check when you're designing the structure. And the big thing about that is that you can't really consider beams on their own anymore. You have to think about the system, so the floor slab plus the beam supporting it to generate the vibration performance. And if you replace a concrete beam with a MiniMass beam and you still have a concrete slab, typically you'd have enough mass still to get a good concrete vibration performance.
Okay, thank you. I think that answers to some extent another question about the dynamic behavior of it. You're talking about it acting as a system.
Right.
Is that right?
Yeah.
Okay, excellent. There's a question there about that there wasn't any reinforcement shown in the legs in your MM02. I must admit I missed that bit. Does that make sense to you?
Good point.
Is that due to the size of the elements?
So it is possible. It is certainly possible to put reinforcement in, and indeed in the bridge that I've been designing, I have decided to put reinforcement in. However, it is also justifiable to avoid it. There are because those legs are always in compression, and so it's a case of checking the various things like tensile splitting and out of plane bending and all of those things. But it's a sort of eagle-eyed viewer. Certainly, when it comes to the bridge that I've been designing, I have put reinforcement in those.
There are so many questions coming in now. I think we'll be answering.
Well, great.
One for you to be able to answer them afterwards. There's a couple. There was one I did want to ask was about the depth, and you mentioned that a little bit with regards when you were comparing the potential lengths and the suitability and the transfer slabs. How does that compare? Because is that
Yes.
something that you can talk about?
Yes. So again, as a comparison, I'm pretty careful to make sure that I stay within the depth envelope of whatever I'm comparing to. But it's worth saying the span to depth ratios that you might be familiar with traditional concrete beams, whether it's span over 20 or span over 15 or whatever you might aim at. It's pretty similar with Minimass. I found that when you have a high live load, you've got to have you've got to tend towards the lower end of that range. So it would be somewhere in the span over 12 to 15 if you have a very high live load. And if you have a high dead load, then you can push it up to span over 20.
Excellent. And I think I'm gonna. There are too many for us to get for questions to go through, I'm afraid. But I'm going to end with the question about very exciting to see a pilot project starting to come through in Ukraine. Any starting to be thought about in the UK at all?
Well, I'm
You're allowed to talk
trying
about
very hard on that, and I have been talking to a developer about a potential pilot project. We're looking at sort of a footbridge on a site, and it seems to me that because it's new, of course, it's hard to get these things started. But something like a footbridge is likely to be the first thing that comes up in the UK, because it's a sort of small piece that we can bite off without scaring everyone away.
Okay, excellent. Well, listen, thank you very much for that, Andy. That was a really excellent talk. And thank you everybody for listening in and for all of those questions. We will share them with Andy, and he will hopefully be able to get back to you with regards to that. And so, just before we sign off, then I'd just like to give some information about the next Fresh Concrete, which is available to book online. That takes place in pretty much a month's time from today, on Wednesday, the 28th of June at 1 o'clock, same time. And this is on low carbon magnesium based concrete, which is carbonite. And there's going to be a presentation by the founder of that innovation and Professor Dr. Thomas Brook from Munich, who is also a co-founder, and he'll be talking about the technology that they've been developing there. So please do sign up. There's the link is available on the Concrete Centre and the Building Centre website for that. And thank you very much again, Andy, and I look forward to some exciting new developments using this innovation, and I hope you all have a very good afternoon. Thank you very much.